and
Okay.
go for it.
Okay, Jimmy, thank you. Those of you that have returned and survived yesterday, I thank you. Obviously, the instructional pace was hectic to say the least. I wanted to get through the information that we did. Um, I can tell you the good news is I'll remind you from yesterday, everything that I talked about yesterday, every slide and a lot more are on the PowerPoints that I'm willing to send to you. About 20 of you have already requested that they will be sent, and I will do that. The rest of you that if you want a copy of all this information, including the two handouts for Al's and my classes, just send me an email, dkrieger.com or dkrieger@consullab.com, and I will be happy to send you a very large PowerPoint with a lot of information in it, along with the one that I did yesterday and the two handouts. So thank you for the bearing with me. It was a rush, 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 and I sorry for that, but we had to get that done. I'm going to share my screen and start the PowerPoint again. Let's see here if I can do this the right way. Here we go. Some of the things that I didn't have time to do yesterday, and I just wanted to explain. Those of you that have owning a U-scope or considering purchasing a U-scope, you do not need to hook a U-scope up to anything to get a signal. It has a built-in signal generator, and you can adjust the frequency and the duty cycle of a simple digital square wave or frequency-based signal, much like a map sensor, digital map sensor. And it comes with the cabling that you see two cables there. The one on the top is for the scope leads, and the one on the bottom, what looks like a little photo jack, is the output of the signal generator. And all I did was bring those two white and black leads out to the green and black scope leads, hook them together, and you will see that signal generator. To see it in real, there it is on my scope, and you can simply go down here to options and you'll see adjustments for signal duty cycle, and I can move that back and forth. You see the duty cycle is changing on the scope, and you can use your cursors to measure frequency and pulse width. And if I go up to frequency, I can make those adjustments too, and the frequency will change. So it's kind of a neat feature that when you're learning the use scope or having your students work with it, it's a neat thing to have a built-in signal generator. Many of you asked about training resources, videos. Would we be willing to do additional classes? The answer is yes, but I want to share with you, if you go to YouTube and you search AES Wave or Picoscope, you're going to get a whole bunch of options. I wanted to point out training videos by Justin Morgan. He does some side work for AES Wave, and here are three excellent, excellent videos. You see, the first one covers hardware, screen, menus, and presets. The second one covers cursors, custom startup, and data management. The third one is sample speeds, trigger windows, and positive zoom scroll. The fourth one is how to set up the use scope for an AES Wave COP or coil unplug wand that you can use. These are excellent videos. These links are in the PowerPoint if you want them. You see the links are listed underneath the captures. However, you can access them from YouTube yourself. Here's one on Scanner Danner. Paul Danner did this when using the U-scope on identifying a misfire. Pete Meyer uh, does one on relative compression testing using the U-scope. So I've included those just for your reference, but there's a lot more available on training on the U-scope. Again, I want to point out that go to Facebook, and if you're not a member of these organizations, might want to consider looking at it. Auto Lab Scope Diagnostics, our Facebook forums, Auto Technicians, professional automotive technicians. They're all, AES has a tech feed Facebook group. Council Lab has one called Council Lab Product User Group. Just search for it and you'll see it. If you own Council Lab products and want to share discussions or ask questions, it's a great place to do that. Of course, Scanner Danner is offering free access to his premium channels where there's hundreds and hundreds of videos available there. AES Wave also has a dedicated site for educators that you may not be aware of, and that's the website or the link to get to it. IETN has thousands of waveforms stored on their archives under knowledge base. However, in order to get the waveform library, you need to be a corporate member, which costs you money. You can join IE10 free, but you don't have access to the waveform library. And this is just one example of the thousands of waveforms that are in there, and it tells you the car it came from and a little bit of information about it. And again, just as a reminder, this was my setup to put on the session I did yesterday. I had the Ohm's Law trainer available to me, my Pico there you see in the middle. The U-scope is setting on a block of wood taped to my desk with duct tape, and above it was my document camera that I'm using, and you see that it doesn't have real bad resolution. And of course, if you jiggle it or move it, you'll see it on the screen. But you can share this with your students, or if you're in a classroom and you want to display what's being shown on the U-scope screen. Someone asked yesterday if you can display live data, and the answer right now is no. I talked to George Minshew last night and asked him about that. He said there isn't physical room inside the case to do what needs to be done to display live data. But using a dock camera or an Elmo or something like that, you can certainly do it. And with that, unless there's any questions, I have finished my section of these classes, and we're going to let Al come in and do his thing. I think you're going to see a great explanation of how the scope, the DSO, can be used to assist students in learning and understanding circuits. And it also gives us examples of how we should be considering either using U-scopes or using DSOs or teaching DSOs or both. They're, as I said yesterday, becoming an essential part of required tools for automotive technicians today. I will stick around afterwards if you have any questions for me or Al. I didn't give you any chance yesterday. If there were questions, I'm sorry I blew by it, but I'm available today and we'll be happy to stick around after the session. And with that, here's Al, affectionately known as the Great Santini.
Oh,
Al.
Oh, that's bad. That's bad.
I'm going to unshare here and
oh my, another good picture too. Well, hello everybody. It's good to be here, and just so you realize it, Dick and I put together DSO programs, and I don't know how many times we've done it, but quite a few. And normally it's an entire day. So when we try to compress it down, it sometimes doesn't work exactly the way. Let me share my screen. Okay. You'll notice that one of the things that I'm going to do, I'm going to spend a little time with on here right away, is I'm going to try to get across how to teach something rather than diagnose something. Now, we're teachers, and hopefully because we're teachers, we have a pretty good idea how something works, but getting across that idea to somebody else is a difficult thing. So what am I going to do? Well, I'm going to spend real little time on how to connect the DSO into a live circuit, but I'm going to spend more time on how to use the DSO to see how something works. This works really well. It seems to work really well with students. Well, obviously measure voltage and current patterns in fuel injectors. My goal is to do 3 different things here. One of them is fuel injectors. Another one is ignition, where there is no secondary and maybe not even any primary available. And then a third will be time permitting. Tomorrow, I'd like to spend a couple times and look at using a current probe on a fuel pump. So that's what we're going to do. We're going to use voltage and we're going to use current. Okay, let's talk just for a second about connections. You have to recognize, if you're going to use an oscilloscope, that wherever you have the ground negative connection, that is considered to be 0 volts. So if you stick it on a stud, which is grease covered on a fender, you know, you've got a voltage drop between that fender and the engine, and maybe even between the engine and the battery. Less likely between the engine and the battery. But it drives me crazy when guys will send me patterns and I look at them and I go, what is this? Where was your ground connection? Well, I was on the fender. Oh, is this a brand new car where the fender's not rusty or anything else? You know, Illinois, we throw salt on the water. Salt and water on the road, and as a result, we wind up with lots and lots of corrosion. The other connection is obviously the signal. I'm not sure you're aware of these PD10s. If you're not, there's the number. Maybe you want to, and maybe Dick, if you wouldn't mind putting that number, or I can even put it into the chat. You know, when I'm done here. The PD10s, they're not cheap, but what they do is they save your car, and I think that's the important thing. Okay. A couple of other considerations. If you have a bad ground, you're going to wind up with noise. Wire routing is extremely important. To get this particular bad pattern, I ran my wires from my 5100, which was an older oscilloscope that I used to have, Vitronics, nice unit, no longer available. But I ran them right over the top of an alternator, and I turned on a whole bunch of accessories so the alternator was working. And what that did is it produced a whole lot of noise. You can recognize noise when you see it, because noise has amplitude and has no time base. Now, by that, what I mean is, if you look at the screen, you can zero in. There's some little peaks that go up and go down, and they have no width to them. That's amplitude up and down, and time base, remember, is from right to left. So if you have that, you're dealing with noise. Okay? Now, many scopes have filters that are available. And just a real quickie thing on what a low pass filter is, and then I'm going to switch over to the Pico. Matter of fact, I'm going to do that. I'm going to switch over to the Pico right now. Okay, Dick's Pico on the screen. Okay, Dick went out to lunch. Anybody tell me? Okay.
I'm here. Your Pico is showing. Yes.
Okay. All right. If I go over, and I don't know if you can see my cursor real well, but I'm going to go over to A, and only A channel is on right now, and I'm going to click on it. And you'll notice right here, about halfway down the screen, is something called low pass filtering. Now, here's the way to think about this. If you take a signal, that signal is, for the most part, is a pretty low frequency filter. Is a pretty high frequency event, and it needs to be filtered sometimes, especially if you're working out in the shop and you maybe got a car on either side of you and the guys got the hood open and the engines are running. You've got signals all over the place. So what you do is you turn on activate filtering, and this is now a low pass filter, which means it will allow the low frequency signals through, but not the higher. And you can control this here. So in other words, I can make it greater, or I can go back and make it less. You'll typically find that in many, many cases, you'll get up to 10 kilohertz, and a 10 kilohertz low pass filter will take out most of the garbage. And that's what you're looking to do. I'm going to turn it off right now because we may turn it back on in a little while. All right. One of the advantages to a digital storage oscilloscope is the ability to be able to use a current probe. And a current probe gives us the ability to look at current, and this is especially useful in ignition and fuel, especially when you combine them together. We'll show you how to use that a little bit today. Okay? When it comes to setting up the probe, you have to realize, and I hope the screen comes out good enough on your, that you have, and this is a pico, by the way, and it has 3 scales. Well, 2 scales and an off. So right now we're in the 20 amp scale, and there's a couple things about it that are important. First of all, the power light's on. Secondly, the low battery is off. Do not ever use a current probe if the battery light is on, because what happens is the accuracy and as the current probe is trying to measure, especially if it's fluctuating, the current draw is also fluctuating inside the current probe. It's got most of them have 9-volt batteries in, and once the battery gets about probably almost only about a third down, then you'll start seeing that. If you begin hearing noise on me, it's the guys. I'm in a Dell Web community, and they're mowing the lawn, and he just went by the window, and now he's coming in the other direction. So ignore the noise. What does this mean? If you look in the parentheses by the 20 amp, it says 100 millivolts over amp. What that really means is a current probe generates a voltage. Well, how much voltage is it going to generate? It's going to generate a 100 millivolt signal or voltage for every amp that it sees. If you close it around something which is bigger, 60 amp, you'll notice that it changes the scale around. Now what you do is you generate 10 millivolts for every amp. How do you do this? Well, let's just take a quick look over at Pico again. Excuse me. And let me go up to here. Okay. And you'll notice in this side over here, there's something that says probe times 1. That's the default setting, and to be honest with you, if you're teaching students, you might as well keep it in that. But know that this unit will also take and put any of these inputs into it. Okay, so for instance, if I'm going to be lower than 30, or if I have a 30 amp clamp, I click on this. Here's a 60 amp clamp, which is what I have in 20 amp mode. When you do that, what happens is it sets the screen up so that it now directly will read amperage on the side. Okay, most of the time what I do is I go standard, and the reason I do standard is it just makes the most sense, especially if a student recognizes the fact that he needs 100 millivolts equals an amp. Okay, now bounce back and forth here a little bit. Okay, when we look at signals and we look at signal analysis, please remember the ground. That ground has got to be good. If the ground's no good, or it's on a rusty old bolt or whatever, it's not good. It will have an impact on your signal. And then obviously the voltage. Using dual channel capability allows you to do some signal comparison. So let's get down to the meat of this though. If I want to teach a student how a fuel injector works, what I try to do is make sure that he knows enough about the DSOs so that because I've taught it very early in a basics class. Now I know that some of you, maybe all of you, do not agree with me, but let me give you my philosophy. You got a basic electricity class, put the DSO into that. And the sooner you get a student using a DSO as a multimeter or as a voltmeter, the better off you are. The next thing is use it for use the patterns so that a student sees what actually happens, and try to get them to the point where the first thing they do is they recognize, how does a fuel injector work? Okay, can I see it work? And the answer is yes, you can see it with a DSO. So I'm going to draw a simplified electrical diagram here in a minute, and then we're going to add a DSO to it. So I'm going to go over to whiteboard. Okay, and just for those of you that are wondering what I'm doing, I've gone to Microsoft Whiteboard, and I have Microsoft Whiteboard set up so that it's in crayon mode or draw. I'm going to click on my red, and I'm going to try to emphasize to the student the very first thing we need is we have to have a battery. We have to have B+. Where does that B+ goes? Well, it goes to a coil of wire. Okay, where is that coil of wire? That coil of wire is inside the fuel injector. And then ask the student, what happens when we put current through a coil of wire, especially if there's some other ferrous material around it? And the answer is we generate a magnetic field. Okay, so what does that magnetic field do? That magnetic field opens the fuel injector. Well, to be able to open the fuel injector, we have to have some kind of a control. And that control, in most cases, means that we're going to put this fuel injector, the negative of the fuel injector, we're going to put it down to positive, or down to ground. Excuse me. Now, please notice what I'm playing with colors here, and I think the colors are kind of important because it's important that a student recognize that if we stick a DSO on here, there's my DSO, and there's my ground. If I put a DSO on here, that DSO right now is going to see a plus. Well, why does it see a plus? Because it looks all the way back at B+, because there's no current flow. And then again, we want to emphasize to the student, what does it take to have this not show that as a plus? Well, it takes closing this switch. So and once we close this switch becomes ground. So now what happens is the voltmeter, or the DSO in this particular case, goes from a plus when there's no current flow to a minus when there is current flow. And again, this is voltage drop in action. And then what is this? Well, this is actually PCM. Okay, and you can label it if you want. Now, usually what I do is I do this on a whiteboard in the same room. And part of it is, I mean, I could put it in a PowerPoint, and you can make it in a PowerPoint. You could do that, you know, put it one slide with B+ and talk about it. But I think it makes more sense, at least it did to me, when I can draw it and I can stop, turn around, look at the students and say, okay, now what happens when that coil of wire? Well, why does this cause a fuel injection to occur and everything? And once the student has a reasonably good idea of that, then the next thing we do is we go over, and I'm just gonna open up fuel injector waveform. Okay. Now, the waveforms that I've stored have voltage and current in them, and I want to look at voltage first. So the very first thing that I'm going to do is I'm going to do one of two things. If you can follow the cursor, I'm either going to do this, okay, and put this out of the way, stick it up here somewhere, okay, and let's work with that. Now remember, and again, you're talking to the student. And you ask the student, you say, well, what's the first thing that has to happen? Well, you know, Mr. S, we have to have voltage. Now, on a Pico, if I go up here to the blue, and then I start dragging it, this is a voltmeter. This is a voltage cursor. I'm going to put that voltage cursor right there. And up at the top, it says, and I'm not sure you're going to be able to read this, but it says 14.36 volts. Ask the student, what is this? Well, you know, Mr. S, that's the battery positive. Okay, so we're seeing the battery positive because there's no current flowing. Okay, that makes sense. What does it take to get current to flow? Somebody in your class is going to say, we have to apply a ground. Okay, let's see if that's a good ground or not. So now we bring the voltage down and we read it. I probably didn't bring it down far enough. And we're down, I'm close enough to zero. I mean, you know, the width of the line here is enough. And now what's happening? Well, what's happening is the fuel injector is injecting fuel. And then the question I always ask at this point is, well, how much fuel is being injected? And they can sit down at the bottom here and they can actually time this out, or we can bring in the other cursors. So there's a time cursor. Whoop. There's a time cursor. Let me get back here and move it over a little bit. There's the time cursor. Bring my other time cursor out, put it at the beginning. Now, when you put two cursors on the screen, the time or voltage in between will be labeled as a delta. So look in the upper side over here, and you can see here that this fuel injector was open for 2.36 milliseconds. So now we have a student looking at, we applied B+, he measured it. When we wanted the fuel injector to actually inject fuel, we applied a ground. What applied to ground? The PCM applied to ground. Now, once that PCM is applied to ground, what's the next thing that's going to happen? Well, the fuel injector is going to stay open. How long did it stay open? It stayed open for 2.376 milliseconds. And at the end of this, and this is the hard part for students to understand, at the end of this, you have to explain to them that what's going to happen here is once we turn this fuel injector off, we have a very large magnetic field that's been holding it open. And it's a pretty strong magnetic field. When that magnetic field collapses, we have magnetic flux lines crossing over a coil of wire, which means we're going to generate a voltage. And lo and behold, what is that voltage? Well, in this particular case, you bring our voltage one up again. That's 116.9 volts. So we have a substantial inductive kick that occurs here. And then there's one other thing that I want you to pay attention to, and I'm going to go back to the main thing. Okay, if you can see, and I'm hoping you can see where I have my cursor, that little blip right there on the current waveform is where the fuel injector opens. This is where the fuel injector closes. And I'm going to come back to this, probably not today. But what I want to do is I want to emphasize this is a very simple car. This is a 2007, not new, a 2007 Toyota. If you make a big mistake, that mistake will be to use something brand new. Okay, here's Malibu. Let's use a Malibu. This is a 2018 or 17 Malibu. Now, that's the actual fuel injector waveform. And by the way, you're looking at only 1 millisecond all the way across the screen. Okay, so it's, there's a lot going on. Think about this. Can you explain this to a student as easily as I was able to explain how a regular fuel injector works? I shouldn't call it regular, an older style fuel injector. These multi-strike fuel injectors are very difficult for students to understand. Hell, they're difficult for instructors to understand. Because the other thing about them is, notice what we've got here. Let's put a voltmeter cursor on here. 63.28 volts. Now, the first question you have to answer, and I'm not going to answer it right now, but the first question you have to answer is, well, where the hell did we get 63.28 volts from? It's a 12-volt car. Okay, so this makes it a little more difficult. And by the way, a little history here. Okay, this again is a 2017 or a 2018. And then let's put a Hyundai up.
2 minutes, Al.
Thank you. This is an older Hyundai. And you can see it doesn't have near the pulses that the newer Malibu had. It's still a multi-strike. And you notice we still have some pretty high voltage here. What are we running? 64.78. And then how long did this fuel injector actually stay open? It didn't stay open as long as you think it might have. Just by looking at it, you say, wow, there's a lot going on there.
Obviously, these are GDIs.
Yes, GDIs, thank you. 1.189 milliseconds. So it wasn't open that long. Okay, now I'm about out of time, and I will tell you in advance that what I'm going to do tomorrow, I'll answer questions, but what I'm going to do tomorrow is going to be to go in and do a little more analyzing. I hit the wrong button here, by the way, that's why I turned it off. I'm going to use a little more of the pico capabilities, and we'll talk about fuel injectors, and we'll also talk about ignition. Okay, so I'm going to unshare my screen if I can figure out how to do that.
I think you accomplished it.
Okay, Jimmy, you can turn the recording off.
I will do that right now.
Right at 1:30. How about that? Dick, did we have any